Hello everybody, welcome to lecture 5. Today we learn the mean value theorem and the consequences of the mean value theorem and how those consequences will help us sketch accurate graphs of a function given its first and second derivatives. First off, the mean value theorem is one of the most important theorems in calculus, and the reason it's so important is because this theorem pretty much proves the rest of the class for us. If we were to take a proof-based approach to a calculus, which all you math majors will do that, you will learn that this is kind of the key statement in a bunch of those arguments. The mean value theorem is hugely important because a lot of what follows comes as a consequence of this. But before we get there, we got to do a few definitions and theorems. So first, increasing and decreasing functions. What it means for a function to increase, what it means for a function to decrease. The definitions are actually pretty straightforward because we know what it means to increase. If you increase, you get bigger. If you decrease, you get smaller. There's no need to involve calculus in these definitions. So f is increasing on an interval I if f of x of 2 is greater than f of x sub 1 whenever x sub 2 is greater than x sub 1 for all x1, x2, and I. A few notes on this. All this says is that the y values get bigger, y goes up, whenever the x values get bigger. So if the x values get bigger and the y values get bigger at the same time, your function is increasing. This is true for all x values inside of the interval. If you just sketch a graph out, since we read graphs from left to right, as x gets bigger, it means you're going this way, and the y value is also getting bigger. Your graph's got to go up. F is decreasing if the opposite is true. F is decreasing on some interval I if f of x sub 2 is less than f of x sub 1, whenever x2 is greater than x1, for all x values in the interval. This means that your y values are going down because f of x sub 2 is less than f of x sub 1 whenever your x values are going up. So x gets bigger, y gets smaller, so that means your graph is going this way. So increasing and decreasing functions, pretty straightforward, common sense definitions, no need for calculus. Absolute extrema. These points are the absolute highest and the absolute lowest points on the graph. So their definition is as follows. Let f be defined on some interval I that contains c. So c is an x value in this interval, because interval I is just some range of x values. F of c is the absolute maximum of f on I if f of c is greater than or equal to f of x for all x and I. So pretty much it's the absolute max if it's the absolute highest. It might be tied, in which case you have 2 or 3 or multiple absolute maxes, but either way it is the highest point on the graph. And the absolute minimum is the exact same definition, it's just now f of c is the lowest point on the interval. This symbol right here, this upside down A, means for all. I kind of ran out of space when I was doing this, so I just used the shorthand for all. So this means for all x in the interval I. There's a few other ways to say absolute extrema, so aka, you could say global extrema, which makes sense. Global is like the whole big picture, and out of all that big picture, it's the extreme value. Or you could just say extrema. If a question ever says find the maximum, it means find the absolute maximum. If it says find the minimum, it means find the absolute minimum. So you don't have to say absolute or global. It's okay to just say find the max. And this implies that the question wants you to find the absolute max. Also note that this is the y value, right? F of c is the y value that corresponds to x equals c. So the absolute max is the highest y value. Like if this was your graph, that's a bad example. There we go. this is the absolute max, this y value. So that corresponds to like y equals 7, the absolute max is 7. And the absolute min, which is not clear on this horrible graph, there we go. The absolute min is -5. So the absolute max and min are the y values that are the highest or lowest points. The extreme value theorem, which is actually, again, a fairly straightforward statement, but it is way beyond the scope of this class to prove. Sometimes the most straightforward statements are by far the hardest ones to prove. In this case, the extreme value theorem, or the EVT, if you are a fan of acronyms, says if f is continuous on the closed interval AB, this has to be closed, then f has a min and a max on the closed interval AV. Pretty much what this says is if you start your graph off with two filled-in points, one at A and one at B, and the one at B could be anywhere, it could be above, equal to, or lower, then let's put it up above. There is no way to draw a continuous curve that does not have at least one max and one min on this interval. Right? It's impossible to go from here to there without having the max and the min. If you go straight there, then here is your max and here is your min. And that, by the way, is why the interval has to be closed. If you had open endpoints there, open at A, open at B, this graph has no max or min. There is neither a highest nor a lowest point on this graph. Like if that was 1 and that was 5, the graph gets as close to 1 as you want from the right side, but never actually gets to 1. And it gets as close to 5 as you want from the left side, but never actually to 5. It gets to like 4.99999, but never actually to 5. So you have to have a closed interval for this to be true. If you do like some crazy curvy line, you're guaranteed to have at least one max and one min. The weird example of this, or at least the most interesting I suppose, is if A and B have the same y values and your graph went straight across. In this case, every single point on this graph is tied for the highest, which means every single point's a max. Every single point on this graph is tied for the lowest, which means every single point's a minimum. So every single point is both a maximum and a minimum, which seems weird, but it fits the definitions because of that greater than or equal to, less than or equal to. This little or equal to thing, which allows for the possibility of ties for the highest or lowest point, is why this is fine. Next, relative extrema. A relative extrema means that there's some open interval that contains C on which f of C is the maximum. Made a mistake when I wrote this up. There we go. So if there is some open interval that contains the point C, and on that interval f of C is the maximum, then f of C is the relative maximum. Likewise, if there's some open interval that contains C in which f of C is the minimum, f of C is the relative minimum. Another word for this, aka, is local minimum. Which makes sense. The global max is the biggest point, big picture. The local max, or the local minimum, is just the biggest in some small locality. For example, let's say we got ourselves a graph like this. It goes up and down, up and down. There we go. So the absolute max is right here. That is the absolute highest point on our graph. The absolute min is right there. That is the absolute lowest. Now for the relative extrema. For a relative extrema, you need there to be an open interval about the point, and on that interval, this is the highest or lowest point. So here is the relative max, or a local max, because in this interval, in between those 2 points, that's the highest value. And this is a local min, are a relative min if I say consistent. Because on that interval, it's the lowest point. This is also a local min. It's the absolute min, but also if we would only look at that individual neighborhood about the point C, it is the lowest point, therefore it's a local min. This point is nothing. It's not a relative max because there's no open interval that contains that point, because there's no right side. So you can't have an open interval about the point, there is no right side. Endpoints cannot be relative extrema. So endpoints to the graph are never local extrema. They could be absolute extrema, but they can't be relative extrema. So this is also not a local max, it can only be the absolute max. And even if you have some weird functions, like let's just make up a cool function. Let's make it so it's not always differentiable. Let's lose continuity. There we go. So here's a sufficiently strange function. The points of interest, I'll call this one A, that B, that C, that D, and then over here is E. So, man, I did it again. Oh, never mind. So A is nothing. I was going to say that A is tied with E as the absolute min, but it's not because this point is lower than it. So A is not the absolute lowest point. It's not the absolute highest point. And it's an endpoint, so it can't be local extrema. So A is nothing. Nothing is going on there. B, if we look at a open interval around that point, this is the highest point, which makes that a relative max. It's not the absolute max because that point's higher. At C, well, this point is the absolute max, as I just kind of gave away, but it's also a relative max because there is an open interval around C, and of all these y values, which are mostly down here, but this one is the highest. So it's a relative max because in this interval around the point C, that's the highest point. So you don't need continuity for a relative extrema. All you need is for your function to exist, which ours does. At D, a very similar thing happens. It's the absolute min, because it's the lowest point of all. But if you check out that interval right there, this is the lowest point. So it's a relative minimum too. Because again, relative extrema do not need continuity. You just have to have an open interval about the point on which your function is defined. And then E is nothing. It's not a relative max, not a relative min because it's endpoint. It's not absolute max or min. Lastly, if f of c is a relative extrema of your function f, then f prime has two options. It's either 0 if your function's smooth. If you draw a smooth function, which means no sharp points, no discontinuities, all good to go. Any relative extrema, the slope is going to be 0 there. The tangent line is going to be horizontal on a smooth curve. Or f prime might not exist. Like for example, say you have like f of x equals x to the 2/3. This graph looks like this. So that right there is an absolute and relative minimum, but f prime does not exist there because it's a sharp point, it's a cusp. So f prime does not exist. It's one of those two things that's got to be true. And sometimes graphs can have a combination of that. Like for example, let's say we got I don't know, f of x equals absolute value x squared minus 9. If we were to graph this function out, it would look like this. Right? It's a parabola where the part that would have been negative is flipped over the x-axis due to the absolute value. So we have 1, 2, 3 relative extrema, 2 mins and 1 max. The maximum has f prime equaling 0, but the two minimums, or minima I suppose, have f prime not existing. This is going to be big for us later on. Relative extremas can only happen when f prime is 0 or non-existent. Next, Rolle's theorem. Rolle's theorem gets its name from a mathematician named Michel Rolle. I'll write that up here, not that it's too important. French mathematician who's actually skeptical of the veracity of calculus. He didn't actually believe that calculus was accurate for the first few decades of its existence. But then he came around, and this theorem has his name. Rolle's theorem. If f is continuous on the closed interval ab, and differentiable on the open interval ab, and if f of a equals f of b, then f prime of c has to equal 0 for at least one c in the open interval ab. So essentially, if you have a continuous and differentiable curve and your endpoints are equivalent for their y values, then the slope's got to be 0 somewhere in the open interval ab. I'm going to sketch this out. So visually, here's A, here's B. The two endpoints have the exact same y value. Rolle's theorem says that a continuous curve that is also differentiable, which means smooth, there's no sharp points or discontinuities, has got to have a slope of 0. And if we were to prove this, which we're not, the proof would just be showing the three possibilities for our graph. The first possibility is that the graph is constant, that the graph goes straight across. If that happens, then you have a constant function, therefore f prime is 0 at every point. So Rolle's theorem is satisfied. The second possibility is that after f of a, the graph goes up. So after a, the graph goes up, but if it ends up right there, it has to go back down. Maybe it goes back down and goes back up, but either way, if it starts up, it has to go down, and it has to be a smooth transition from positive slopes to negative slopes in order to be differentiable. That gives you a relative extrema. In that relative extrema, f prime has to be 0 if it exists, because f prime exists for Rolle's theorem, which means that's not a possibility. And the third possibility to consider when you prove this is that the graph goes down after A, in which case it's got to go back up, and when it does, you have a relative extrema, thus giving you a slope of 0. So that is Rolle's theorem. Rolle's theorem is really only useful to us because it is a weak version of the mean value theorem, but it's easy to prove. So pretty much when we do prove the mean value theorem, we're going to use Rolle's theorem to do it, because Rolle's theorem is easier to prove. Just got to show those three cases, which is why it's useful. One last note before I stop this clip. This part right here, differentiable on the open interval. Sometimes students wonder, how come we need continuity on the closed and differentiability on the open? Well, we could have differentiability on the open, but you don't need it. That is a more strict condition. But since you don't need that to be true, we keep the most general version of the theorem possible. Whereas you have to have a closed interval for continuity. If it was open, this is no longer valid. But differentiability, excuse me, you don't need the closed part. As a quick side note, if you were differentiable on the closed interval, it means the slope from the left and the slope from the right match the slope at those 2 points. But that's harder to show, harder to prove, and we don't need it, so we don't worry about it.